You ever wonder how an online store can find that one specific product you're looking for out of millions in like a split second? Well, it's not magic. It's actually a powerful secret language working behind the scenes. And today, we're going to pull back the curtain and look at the simple building blocks that make every single complex database query possible.
Yeah, you heard that right. It sounds super complex, but it really isn't. Every single thing a database does, from finding a friend on social media to processing a massive financial transaction, it's all built from just 6 fundamental ideas. Think of them like the atoms of data. And by the end of this, you're going to understand every single one.
Okay, let's dive in. Before we can start building anything, we need to understand our materials, right? We need to know what we're working with. So, welcome to our little data playground.
First, just a little bit of vocabulary so we're all on the same page. In the formal world of databases, we don't really say table. The fancy word is a relation. But don't let that intimidate you. It's just a grid of data. The columns, we call those attributes. And the rows, those are called tuples. That's it. A relation is our basic piece of clay.
So, throughout this whole thing, this is going to be our go-to example, the sailor's relation. It's super simple. It's got 4 attributes, a unique ID for each sailor, their name, a skill rating, and their age. We're going to use this simple little table to ask some surprisingly powerful questions. So our first set of tools is all about working with just one table at a time. I want you to think of our sailor's table as a big block of marble. These next few operations, they're our chisels and our hammers. They let us carve away the pieces we don't need to reveal the beautiful data sculpture hidden inside.
Our first tool is called selection, and it's represented by the Greek letter sigma. Its job is incredibly simple. It chooses which rows to keep. You give it a condition, and it just filters the table, keeping only the rows that match your rule. It's like a horizontal slicer for your data.
And here's a perfect example of that. Let's say we want to find all of our top-tier sailors. The ones with a rating greater than 7. The selection operator just goes row by row, checks the rating column, and keeps only the ones that pass the test. And what we get is this new, smaller table that only has our most skilled sailors. Okay, our second tool is projection, represented by the letter pi. Now, if selection slices horizontally by picking rows, you can probably guess what projection does. It slices vertically by picking columns. You just tell it which columns or attributes you care about, and it gets rid of everything else.
For instance, what if we only care about the sailors' names and their ratings? We don't need their ID or their age. We just apply a projection. It takes our original 4-column table and spits back this new, leaner 2-column version. All that extra info is just gone.
Now, our last single table tool is the simplest one, but trust me, it's absolutely essential. It's called rename, represented by row, and all it does is let you give a new name to a table or to its columns. Think of it like a label maker for your data, which, as you'll see, becomes critical for staying organized when things get more complex. Okay, get ready, because here is the first big aha moment. Do these ideas, filtering rows, picking columns, do they feel a little familiar? Well, they should. Selection, the thing that filters rows, is just the where clause in SQL. Projection, which picks the columns you want to see, that's your select clause. And rename, that's just the as keyword. See? You've probably been using relational algebra this whole time without even knowing it.
So sculpting one table is pretty useful, but the real, honest-to-goodness power of a database comes from connecting different pieces of data together. So let's level up and look at our next set of tools.
All right, the first couple ways to combine tables are union and set difference. Now there's a catch. They only work if both tables have the exact same column structure. Union basically just stacks one table right on top of the other and gets rid of any duplicate rows. And set difference, it takes the first table and removes any rows that also show up in the second one. It's kind of like simple addition and subtraction, but for tables.
But that's the easy case, right? The really interesting question, the one that databases have to solve all the time, is this. How do you connect information from tables that don't have the same structure? Like, how do we link our sailors table to, say, a reserves table to figure out which sailor reserved which boat?
Well, the answer starts with an operation of just pure, unadulterated brute force, the cross product. This operator does the simplest, most exhaustive thing you can possibly imagine. It takes every single row from the first table and pairs it up with every single row from the second table, creating every possible combination, whether it makes sense or not.
And this is exactly what that looks like. If we have 2 sailors and 3 reservations, the cross product gives us a new table with 2 times 3, so 6 rows.
Sailor 1 gets paired with all 3 reservations, and then Sailor 2 gets paired with all 3 reservations. It's a complete combination, but it's messy.
Now, for tiny examples, this is fine, but it gets out of hand really, really fast. If you have 100 sailors and 1,000 reservations, the cross product just generated 100,000 rows, and the vast majority of those are totally meaningless, like pairing a sailor with a reservation that they had nothing to do with. So this isn't the final answer, it's just a messy first step. So, what's the smart way to do this? This right here is the secret to how databases really work their magic. A join, which is the most common way to combine tables, is just a combination of the tools we already learned. First, you do the brute force cross product to create every possible pair. Then, you immediately use selection to filter that giant messy result, keeping only the rows that actually make sense, the ones where the IDs match up. It's just a combine then filter strategy.
Okay, we now have all 6 of our fundamental building blocks, so let's put them all together and create a blueprint that shows how a real-world question gets translated into the language a database actually understands.
Here's our mission, a very common kind of request. Find the names of all sailors who have reserved at least one boat. Now to answer this, we obviously need to connect 2 different tables, the sailors table, which has the names, and the reserves table, which has the info about the reservations.
And this slide, this tells the whole story. Over on the left, we've got the nice, clean SQL query that describes what we want. But on the right, that's the step-by-step blueprint the database is actually going to follow. Step 1, do a cross product of sailors and reserves. Step 2, use selection to keep only the matching IDs. And Step 3, use projection to show only the names. One side is the question, the other is the recipe for the answer.
And this is really the key takeaway of this whole thing. Relational algebra is procedural. It's a precise, step-by-step recipe that tells the database how to build the answer. SQL, on the other hand, is declarative. With SQL, you just describe what you want in the end, and you trust the database's smart internal brain to figure out the best, most efficient recipe to get it for you.
So there you have it, relational algebra. Just 6 simple operations: selection, projection, rename, union, set difference, and the cross product. These 6 ideas form the logical bedrock for pretty much every database on the entire planet. And it really makes you wonder, doesn't it? If these few, simple building blocks can power systems of such immense complexity, what other massive systems out there, in technology, in nature, maybe even in society, are also built on just a handful of surprisingly simple rules?